Uh, Hey guys, this is Priyadarshan, and today I'll be taking you guys through the custom implementation of a CUDA enhanced neural network. So, before we get into the specifics of the CUDA enhanced neural network, let's just recover over the basics of what CUDA is and what exactly it's going to help accomplish in accelerating neural networks. So, first of all, we're going to take an introduction to CUDA. So, what first before we look into CUDA, we have to know about what a GPU is. A GPU or a graphics processing unit is a special type of processor that was originally built for drawing images and graphics on screen. So, unlike a CPU, which only has a few strong cores, a GPU has thousands of smaller cores and is designed to handle many small tasks at once. So, looking more into what a GPU is, GPUs today are not just used for graphics, but they're also used for scientific computing, AI, and data analysis. So this is known as GPGPUs, which is also termed as general purpose graphics programming units. They are powerful because they can split a large job into thousands of pieces and process them in parallel, making them much faster for the right kinds of tasks. We'll look into more about this splitting a single job into thousands of small pieces and processes much later. So, CUDA. CUDA is a technology created by NVIDIA that lets us use graphics processing units for more than just graphics. It allows developers to run normal computing tasks on GPUs, which are usually much faster at handling many small tasks at once. Why do we need CUDA? Traditionally, CPUs are powerful, but handle tasks mostly one after another, which can be slow for big problems. GPUs with CUDA can split the same problem into thousands of pieces and solve them at the same time. So now, comparing a GPU versus a CPU is like a skilled worker who focuses only on one task at a time, carefully and in order, whereas a GPU is a team of helpers who may or may not be as skilled individually, but they can work on thousands of small tasks together. Now, I will show you guys a small video demonstration. Let me show it to you guys in just a minute. Now, this is going to be a video demonstrating the power of GPUs. Now, a GPU is going to be a chip that mainly does graphics processing or many arithmetic operations. Now, for a video game like Mario, you would have to do 100 million calculations per second to render all these details. And this was back in 1996. And as we get along, we have to do 540 million, 2.25 billion, 100 billion for the game Minecraft, which is released back in 2011. And moving on to something more modern titles like Cyberpunk, you would have to do approximately around a trillion or 36 a trillion operations per second. That is how much processing you would have to do to actually render all the stuff in those video games. Now, how does a GPU accomplish this? Or to give you guys a better analogy of how much computing a GPU is doing, if every single person on the planet was doing a calculation of that size, then we would require to do at least 36 trillion calculations. A single GPU, we would need, the earth equivalent of 4400 earths to perform the same tasks as a single GPU to process 36 trillion calculations per second. So that is the power of a GPU. Now you can understand that GPUs are highly specialized and are very, very, very powerful devices capable of processing millions and trillions of operations per second. So moving along, this is the architecture of a GPU versus a CPU, and you can see that the CPU is built more for general purpose tasks, whereas the CPU is built specifically for arithmetic control and operations, basically parallel computing tasks. So where does CUDA fit in? CUDA is the bridge that tells the GPU how to handle tasks that are not graphics related. Instead of showing images, that GPU can now solve problems in science, AI, or data with CUDA. So threads, these are the smallest workers. This is the part where we explain about how threads and the blocks, or how a GPU basically splits a single job into multiple smaller jobs. So a thread is the smallest worker. A block is a group of threads, and a group of blocks is known as a grid. So as you can see, the memory layer key is given over here. There is a grid followed by a bunch of blocks, and each blocks contains a group of threads, and each thread does one single arithmetic operations per second. So, how does CUDA work in simple terms? So given an array of some n numbers a and another array of n numbers b, and we have to find their sum, then each single value in the array can be calculated by using a single thread. So which means you would require n threads, but the whole computation would be done in less than 1 second. So, an example in daily life would be, imagine washing a huge pile of clothes with only one person. It takes forever. But if you have hundreds of people each washing one piece at the same time, the job is done very quickly. That's how CUDA uses threads. Now, CUDA has multiple benefits, and it's being used in a lot of different places, such as training neural networks, handling large data sets, deep learning frameworks, real-time AI, efficient backpropagation, and foundation for AI progress. Now, this is the structure of a CUDA code. Now, let's go and look at how CUDA is actually used in neural networks. For that, here is the actual code implementation of a neural network. First, let's look at a simple CPU implementation of a neural network. Here, we are going to be using C++, and we are going to be training our neural network on a simple XOR with a topology of 2, 2, and 1. So, looking back into the code, the first part that we will actually define is a class called as training data, which we are going to be using to read all of the data that is given in our training data.txt. Now, this is an important parser as it helps us to efficiently read all of the data that is in our data set and pass them to the neural network for processing. Next, we will define a struct known as connection, which contains the weights and the delta weights. Now, this connection is the connection between the neurons in a neural network, and then we will define a class known as neuron. Now, a neuron is a single processing unit of a neural network. Now, it has a lot of parameters, such as the neuron, the constructor function. Then we have various functions to set its input value, output value, and we have all the core functions such as feed forward, calculating output gradients, calculating hidden gradients, and updating the input weights. And we have several private variables such as the bias, the gradient, and the learning rate, which we can dynamically control for each and every single neuron. Now, once we have assigned or defined our single neuron, the next task will be to assign its function. Now, for each neuron, we are going to be assigning its output weights, which will be a random weight, since a randomized start to a weight is a much better neural network than zero weights. Then we are going to be defining our transfer function, which is going to be the sigmoid transfer function over here, and then we're also going to use its transfer function derivative, which we'll need during backpropagation. Then we have several functions to update the input weights, which follows the classical input weight formula, in weights update formula, where we use the old delta weights and the new delta weights, and sum it up as a product of the learning rate and the gradient. And this part over here is basically used to calculate the gradients or sum of gradients for the hidden layers, or the gradients computed in the hidden layers. Since for the output layer we compute the gradients by taking by following the delta rule here, and for the hidden layers we'll be using the gradients propagated from the output layer. And then we have a feed forward function, which basically does the feed forward task, which is the vector dot product operation between the neurons from different layers. And once we do all of that, we also define a net class, which basically controls our whole neural network. And the net class goes through every single layer and calls the feed forward towards the next layer, and then it also calls the back propagation operation. And each network has a private variables layers, which is the individual layers, and the total amount of error accumulated by the network, and the average error and the average smoothing factor. So once we do that, we can help define our layer, which basically we read the topology that is given in our previous section and help define a neural network based on that. And secondly, we have a feed forward function, which we call on the individual layers from the point of the network. And once we do all that, we have a back propagation, wherein first we take the output layer and then we calculate the error using the delta rule, which is the error. The delta rule here specifies the desired minus the the calculated computed error. And then we will normalize our error, and we'll take our average error, and for each point in the output layer we will calculate the output gradients, and then after that we will calculate the hidden gradients. Now, once we have our output gradients and our hidden gradients, we can then promptly proceed to the update the input weights, wherein we update the weights for every single weight value in the entire neural network. And then we have a few functions, few helper functions to get the results and show the vector values. Now once we do all of that, we can finally, in the main function, we can call all of the functions that we have defined above, and we can set it for around 5000 epochs, where in each epoch we are going to be loading our training data, doing a feed forward, getting the result, and then we are going to be back propagating. And for every 100th epoch, we are going to be printing the average error. Now running this program over here, we can see the outputs in just a second. Let the program run, since it is a big heavy program, and it has to set up all the neural network parts. Now here the neural network is working as expected, and for 5000 epochs, every 100th epochs, you can see the amount of error it is printing. At the start, if we go, we have a large average error, which is 0.4. At least 50% of the values are being misclassified. But as we go from epoch to epoch to epoch, we can see that our error is gradually reducing: 0.11, 0.10, 0.9, 0.6, 0.4, and then finally we've ended at 0.03. And if the training time is takes around 6080 milliseconds. Now if you look at the final outputs, our input is zero point 0 and our output is 0.04, which means the output value is as close to 0 as possible, which is our expected target. Whereas if we see for some inputs like 0 and 1, our output value is 0.963722, which is as close to our target 1 as possible. We can definitely round this off to reflect as 1, but it is much better to keep these values so that we can reflect how precisely our network has learned to understand the values. Now once we have seen how neural network is computed on a CPU, let's go and look at how it is done in a GPU. Now for GPU, the overall process mainly remains the same, except that this time we will be doing two core processes, which is we will be loading the data onto the GPU, and then we will be computing the process on the GPU. Now to abstract some of it away, we are going to be looking at the core GPU processes. Now each process in a GPU is computed using kernels. Now, before we get into kernels, we obviously have our helper functions, which is the activation function and the activation function derivative. And here you see we have specified a little specifier known as device, double underscore device. This means that this is a function that is meant to exclusively run only on the GPU. And to clarify terms, device here means the GPU, whereas host means the CPU. And over here, we have another specifier known as global, wherein we define this whole function to be run both on the G. It has to be called from the CPU, but it runs on the GPU. Now over here, this, as you can see, it is called the feed forward kernel, and the feed forward kernel does the exact same process that we looked over in the GPU, which means it does the vector dot product operations. But here the thing is, it does it on the GPU, and by that means it is way more computationally uh, efficient, and it does it in parallel processing. And we have also added a few tricks by using shared memory so as to make the processing much more faster. And these are all the different CUDA programming tricks where we specify each thread within a block for a single neuron. And our feed forward model is neuron first, which means each thread is a single neuron, and each thread will compute the value into weight values for the neurons it is connected. So if a layer has 6 neurons, then we will launch 6 threads, and each thread will act as a single neuron computing its own values. In that way, we can get all the outputs for a single layer in one single second. Now moving on, we have our compute delta function, which is basically, we are going to compute the error, which is the target minus the predicted, and this follows the same principle as the previously explained feed forward neural network. And then there's the compute output gradients, wherein we are going to be computing the gradients at the output layer, and then we're going to be computing the hidden layer gradients. And once we do all of that, we can finally update our weights based on the weight update rule. And this is also another helper function wherein we compute the RMS error. And once we do all that, we can also update our bias, and this is our random weight function. And then we've also follow the same formula as last time, wherein we have a bunch of layers, and then there is a whole network which connects all of the different layers. But the only thing is that we have to write a special function called allocate on device, which allocates the values for the weights, bias, output, delta, gradients, and previous delta weights. That means all the variables necessary for a neural network to perform, we allocate a space for them inside of the device. And once we do all that, we also need to iteratively also define a free device memory function to free up all the memory that we have used. And once we do all that, we can have a function on the layer level to call feed forward for every single neuron in the layers. And once we do all that, we can initialize our neural network. We can also allocate and free our buffers, which is the various input sizes, target values, RMS values. And we also do a memory set and CUDA malloc over here. And once we do all that, we can call our feed forward value, which basically goes through each layer in the layers and calls feed forward layer by layer. And back propagation follows the same value, wherein we compute the delta at the output layer, we compute the RMS error, we compute the output gradients, and for each layer from the back, we are going to be computing the hidden layer gradients. And once we have computed our output gradients and our hidden layer gradients, we are going to be back propagating those errors from the last layer to the first layer by calling the update weights function and the update weights kernel and the update bias kernel. So once we do all that, and when we run this program, this will be the output that we're getting. And this one is going to be vastly superior and vastly faster than our CPU implementation of it. And it also has much more higher precision, since we'll be using FP32 compared to the CPU's FP16 version. So we'll be able to calculate values more precisely, and that helps us to find much more complex patterns given in the data. So let this program compile for a minute over here. As you can see that it's a heavy program that takes a bunch of time to load, since we're basically copying all of the data from our neural network and then passing them off to our GPU, and then the GPU will load. So this might be the only downside, so you have to load a lot of data. So the amount of time spent loading the data might actually be significant at times. So as you can see, it's completing epochs over here. And after all of that, you can see that the outputs for the neural network are given here as follows. And you can see that this time it is focusing much more closely, and the amount of training time that it's taken for it is significantly less. Now, looking at one more implementation of it, which is a rather creative and fun usage of neural networks uh, over here. Yes, so this is an interactive example. Let me just show you guys how this interactive example works. Basically, this, I think, explaining does most of the talking here. So let the program compile, and as it compiles, I will explain to you guys what the beauty of this program is. It basically uses SFML, which is the soft management graphics library, which is a very simple C++ graphics library, but it can help you do a lot of different innovative things, and basically help provide an interactive learning source for people wanting to understand how GPUs and neural